Hey, have you guys heard about the new Parker Sporlan S3C case controller? Contractors, how about a case controller with a one-day setup, access to more data, and efficient system operation for the end user? The S3C series of case controllers provides contractors and store owners automated configuration and network integration. You can maintain precise food temperatures without supervisory control. Easily monitors to prevent product loss, and Bluetooth provides a local connection with the TechCheck mobile app. The series includes case controller display module, a valve supporting open protocol, communication via BACnet and Modbus. Sporlan's mobile app, the TechCheck, allows communication with the S3C case controller to enable proof of work, diagnostic, and data sharing. The S3C communicates with building automation systems and works with Sporlan's SPW series of pulse width modulation valves, also the SSR series of electronic expansion valves. Visit Sporlan.com for more information.
Hi guys, welcome to the Advanced Refrigeration Podcast. I'm Kevin Compass, your host, with Brett Wetzel and our special guest tonight, Mike Squires. Tonight we're going to be going over some more advanced CO2 stuff. We're going to be going over Transcritical Defrost, going over some service-related stuff. We'll touch on some ejector stuff and just go over some experiences we've had, and I kind of bring Mike in. Mike's got a ton of CO2 experience, probably more than most guys in the U.S. have ever been exposed to. So, Mike, do you want to introduce yourself?
Yeah, how's it going? Mike Squires. Live outside of Toronto, Stony Creek, Ontario. Working refrigeration 22 years or so. 23, I think, this year. See, I've been around CO2 since, well, I first got interested in it around 2008 or so on the books. And my first hands-on was in 2011 with my current employer, and we got into the Transcritical systems in 2013, and haven't looked back since then. Really, I've been around it. It's been part of daily life ever since then. We did have the first Transcritical system start up in Ontario, not in Canada. There was quite a few in Canada, a lot in Quebec prior to that. They've been leading the game in North America for sure in that part of the country, and just been around the system, seen different changes and different evolutions with service procedures, installs, and different equipment, and things come and go with it. And to me now, it's kind of, I look at it as, what was new, and it's kind of somewhat normalized now. We're getting our heads around it, and it's not so much of a new thing. It's just a different thing. Like, you'd have an evolution from single units to racks, and then racks to glycol rack chillers, then to regular racks, and then to now we're just CO2 and CO2 systems, and they're kind of somewhat regular now. And yeah, albeit they are a little bit more complicated and a little bit more of a learning curve. But I find once you get over the differences and apply what you already know elsewhere, you can pick it up fairly quickly and look at that. So I guess that's summarizes it a little bit.
Awesome. Yeah, really appreciate you coming on. So first thing I'd like to go over, we kind of went over how the flash tank and everything operates, and we went through like the entire operation of like a standard transcritical rack with a flash gas bypass valve and a high pressure valve. So I kind of want to go into parallel compression next, and could you kind of explain what parallel compression is? I mean, you guys get a lot more of that than we do. So I have a few racks that are parallel.
Yeah, so pretty much what you have for parallel compression, it's almost like an additional suction group. So your vapor compression cycle of your compressor can run a little bit more efficient. It's kind of similar to a family rack or a dual temperature rack where you'd have medium temp compressors and low temp compressors. You're not going to run your whole suction header at minus 20 if you got 50% of your load at plus 20. So you split your header and run a second suction group. So if you had a parallel compression system with a booster system, you'd essentially have 3 suction groups. You'd have your low temp suction group. You don't need to have a low temp. You can have medium only, but you'd have a low temp suction group sitting at minus 20, give or take. Say you'd have a medium temp suction group running at 20 plus 20 Fahrenheit, and you could have a third suction group, which would be upwards to 35 or 40 Fahrenheit. And that third suction group is your flash tank pressure, pretty much. So you use a compressor suction group to maintain your flash tank pressure. So you gain efficiencies by running lower compression ratios on your third suction group or your parallel suction group for the flash tank. So you'd gain efficiency with that instead of just pushing all your flash gas that you need to remove from your flash tank into a plus 20 suction group. You're putting that into a plus 40 suction group. So you gain efficiencies there and energy consumption. So that's where you get that. So with when you have systems with high flash gas loads, especially when you run warmer temperatures more throughout the year, it really pays off to have the CFM of all that flash gas going into a higher suction group. So that's pretty much the basic principle of it.
Yeah, I mean, it's basically to reduce energy costs, especially in like a higher ambient climate, correct?
For sure.
Yeah. And we only have, I think, 2 parallel compression racks. I mean, they're both Carnot racks. I haven't seen Hill or anybody else do it yet.
I've seen Hill drawings with it. They apply it, but it's like every manufacturer. They'll build whatever you pretty much, if they have it down, the leaders anyhow. Like you got your people that will design systems to be the most efficient. So, or I guess leaders or trailblazers in the systems. Like if you have OEMs that just want to build something that they've proven or they have out there, which is you might have companies like that may stray away from those type of projects, but I know Hill Phoenix offers that. I've seen it in their brochures. LMP systems, I'm pretty sure they have them. I haven't seen an LMP one yet, but again, here in Canada, our climate, it's okay for parallel compression, but it's not our ambient year-long ambient temperatures you don't always get the gain for what you have to invest to put into it out of the parallel compression system. But in the southern US, I'm sure it's very common.
Yeah. How many days a year are you guys transcritical roughly?
There's never a full day ever. It'll never stay that long. We get certain times where we'll get numbers of hours. We'll get an 8 or 10 hour stretch during a day where we're running above, we're above 87 condensing, or ambient temperature out, and usually it cools down at night, and you get that. It's a relief from that. So I know it's there's so much data out there to be had, especially if you're working. A lot of our systems use the microthermo system, which it's a fantastic, it's a controller and it's a fantastic data logger. So there's so much data you can get and so much modeling you can do with the information you can pull out of it. You can pull out just data. I recall one instance where we had a 4 transcritical compressor system, and I did compressor proofs, and I think it was 20 minutes consecutively that there was all 4 compressors running, and that was in a 365-day period. So there was, the capacity was there, which I would have to add that system was designed for a dry cooler, but we had it on an ambient, on a adiabatic condenser. So that helped the design. We have 4 compressors. There's only 12 minutes a year or 20 minutes a year that were all on at the same particular time, and they were probably only at a 1 minute stretch per. But that was helped by an adiabatic condenser. But I don't really can't pull off the off my head how much hours or time we have in Transcritical. But when we size that stuff, we use the I guess the ASHRAE bin data, or the data you get from just from the history for the area that we live in. That's where you would judge or you design how much time you're going to be running in a transcritical mode.
Yeah, before I get too far behind here and lose you guys totally, I had 2 questions. One, is there any specific equipment that has to be added to the system when you have multiple parallel on the rack on the Transcritical, or is it just like a regular conventional HFC, as far as there's no other extras that you need to have?
Well, you're still going to have your standard bypass feature. So you're going to still, from what I've seen, the systems I've seen, you're still going to use your flash gas bypass into your medium temp suction group, but you're going to want to have the programming for that not to fight with the parallel group. So, as a bypass for that, and also with that in for some of the parallel systems we have in the winter, I guess November on, it's pretty much the parallel compressor section is almost shut down. It's just not in use. You can almost winterize that system, which is it's tough to have a system with a compressor idle for so long, because we all know the service challenges that has. But it's another reason why the parallel compression isn't always the best opportunity up here for year round, because we have to design for -20 to 110 here. So we have probably similar to what Kevin deals with in his area, that the span from the ultimate lows to the ultimate highs can be pretty tough, which is it's hard on refrigeration design. So as far as additional equipment, it's really a second suction group, and like anything with the suction group, if it's multiple compressors or if it's a single compressor, you'll want to have tighter control. You really want to have really good control, like whether it's a VFD or with digital operation. Now digital type unloading of cylinder heads it's out there right now. I know Bitzer has it. I'm not sure if Copeland has it, and I'm not sure even if they have UL on it now or if it's released, but I haven't seen it in the field yet. But VFDs for sure. We've seen that on the parallel compression side. It's almost mandatory, because you can imagine you're not going to cycle a 20 horse compressor on and off to maintain a receiver pressure. It'll just be it's kind of silly, but you're going to want to very very airflow.
That's the other thing you need to be able to keep that receiver pressure like steady. Like with the flash gas bypass valve, every CO2 rack that I've ever seen have tons of issues usually ends up having the first issues that on steady receiver pressure, like going from more than 10 pounds, I would say, is kind of excessive, swing on the receiver. I've seen some racks where they swing like 85, 90 pounds. That's in the flash gas bypass valve. I've never seen one that swung that much on a parallel compression rack. We only have 2 of them, and they're way up north. So, and we only run the parallel compression when it's like 80 plus degrees outside.
Mm-hmm.
But what would you say like the average swing is on the receiver if you had to look at it with a parallel compression? Is it just as tight, or is it?
It's pretty good. From I've seen one that we do have one. I did see that didn't even have a VFD, and it was almost to the point where was that system. I'm trying to think. Yeah, I think we botched the parallel compression on that and opened the third compressor up and ran it all as one suction group, because you couldn't maintain with it just straight on-off control. It wasn't possible to get a good good pressure control on that receiver. So we basically eliminated the parallel control on that, parallel compression on that, and kept only the 2 suction groups. Other systems with the parallel compression and the VFD, it's in there. It ramps up and down, and it keeps you in a 10, 20, 10. It depends on the. Once the suction pressure is on there, the VFD, it gets on there and it ramps up and down, and it maintains a little bit of a okay, I'm just stipping on my tongue here. When the flash gas load was higher, it maintained a lot better than when the flash gas load was lower, if that makes sense. Because, well, when there's a lot of CFM coming off that receiver, the VFD was able to keep it tighter because the compressor itself was a big, I think it was a 4H TC20 Bitzer, which is, can move a lot of gas. And once it gets to the borderline, it's kind of, is working on with the VFD going down and then coming up. It was chasing it a bit, but again, like everything like that, it's all into the time of the tuning and getting it to fight to work well together. So in the summer, when it's there and it's needed, it holds it pretty tight.
Yeah, that's basically the more time you put into tuning these systems, the better results you're going to see out of them.
Yeah.
So I guess we can move on now to we'll move on to hot gas defrost and kind of go over that. So I've seen a couple different ways of doing this. I've seen kind of like how Carnot does it at a low temp. It's, I guess you would call it cool or latent gas. It would be like a latent gas defrost, and then on a low temp it would be kind of below freezing hot gas defrost. Is that kind of how you would explain it?
Well, see, the thing is with hot gas and the CO2 is kind of tricky because you're dealing with your pressures are your enemies. If you had no holds barred with your pressure, like we've got, I know you've got one, Kevin. We've got a couple up here. Actually, no, there's no hot gas in that one. But if you have a fully like a 90 bar rated system where you can run normal pressures or whatever pressures you have, but in typical supermarket application, the cases and a lot of your piping, and pretty much everything outside the rack room is not high pressure. If it's either a 600 psi max operating or a 650 psi. So if you look at even the max operating pressure, your saturated temperatures are not far above freezing. I think freezing is 0 Fahrenheit is 550 or 520. I think I can't remember off the top of my head, but where is it? I had it here. Fahrenheit. 32 psi, 32 490 pounds is freezing. So what we're used to with HFC hot gas defrost is your saturated temperature of your hot gas or cool gas is the TD from melting ice to that gas pressure is so it's huge. You've got a lot of BTUs to move there. So with the gas defrost and CO2, you're so close to freezing with saturated, so you got to use a lot of sensible heat, and then you can't rely as much on latent heat because you don't have the temperature difference there. And when you're working with sensible heat, you gotta move a lot of gas, and when you got to move a lot of gas, you got to worry about pressure drops. And so with there's a few hot gas systems. Our first transcritical system, I think, would have been or if not the first one that Hill Phoenix tried over here in North America back in 2013, and that takes hot gas from the low temp compressors and pushes it down the suction line in a reverse manner. It bumps up the pressure with a defrost differential regulator, and it comes off in kind of a normal hot gas fashion and puts it down the suction lines, and you're getting close to you're getting at or over 500 psi, or well over 500 psi for gas pressures, and closer to 600 psi to put that hot gas down the suction line. So you got you're a few degrees, 10 less than 20 degrees difference between freezing, and so the hottest it can be saturated would be 20 degrees Fahrenheit, I guess. No, sorry, 40 degrees, 40 or 50, and so you're relying a lot on your sensible and the speed of that gas moving. So it's not quite the same effect you get all the time with your hot gas. It's a little bit closer with the Hill Phoenix model that we see with the reverse flow and coming off the low temp suction. We've had good luck and good experience with that after some trials and that. But I guess the main point is that the what you know and feel and are used to with HFC systems and hot gas defrost is not exactly the same as from CO2 to HFC systems, and it goes all down the line when it comes to piping of cases and lineups and defrost times, defrost termination times. They're all going to be different. So that's an area of difference.
Yeah, I've definitely seen the defrost termination thing. Like it's taken a lot longer on for term temps. It's been kind of like a trial and error for term temps because it's been obviously longer. I haven't seen that Hill Phoenix style. Like most of the stuff I've seen with hot gas has been Carnot, and it's been counterflow. It's been through the liquid line, and then pushed back through the suction.
Yeah, the source of that hot gas would be the same as would it be on the Hill Phoenix system I'm talking about. The pressures are typically lower, depending on the system design of whichever rack you're working on. So if some could be lower than others, but with that system, it's more to do with speed and sensible heat. So that system works well. Also, there's a lot of other systems that can give you problems with that, and it has to do with restriction of flow, because where you're dealing with the sensible heat, you need the flow. So you can't have high pressure drops in your system, whether it's through a distributor or through a dryer or a solenoid, the expansion valve. So with that system, they take the hot gas off the low temperature compressor discharge. They send it down the liquid line. They close the liquid line solenoid, send it down the liquid line to the case. The expansion valve opens to 100%. Typically, they have to be. The expansion valves are well oversized for the refrigeration load. The expansion valves are sized for the defrost flow, to maximize defrost flow into the case. And it goes into the evaporator through the TX valve and back to the suction header. The suction line stops, and there's a return path flow to the flash tank with that gas. And if you don't have a pressure drop and all your piping sizes are okay, that system works well. Again, we've got a lot of those systems out there, and they've been working for once the setup and they're tuned in, they work good. We've got a bunch of those going since, I think our first one of those was in 2015. So they work well once they set up. But it's when you start dealing with bigger cases or evaporators with distributors, you run into problems with that. For example, if you have a 12-foot island case that, like a Hussmann 12-foot island case, if it would have 3 evaporators, could work better than one that would have one large evaporator, because you probably got a distributor and a few passes with a 12-foot evaporator. So that kind of stuff, when you increase the pressure drop on your hot gas flow through it, it restricts the flow of the gas. So through the defrost.
I've definitely seen on the larger coils. I mean, they typically, especially in the wintertime, they typically run the full length defrost, no termination. I mean, they barely hit term. But I mean, other than that, the cases and other stuff, I mean, with that style defrost seem to work great.
Yeah. So one of the other positives with that type of a system, where you have your expansion valve, you can actually set them up and tune them as you would a balancing valve in a glycol system, which it gives you a little bit of power to manipulate the system. For example, if you have a lineup of 6 cases on one system, and one case is further than the other, or just say one case is 10 feet or in a 30 feet on the other side of the store, which is not the best, but we know what happens. You can actually adjust all your EEVs to open at a percentage that you want. This is with a microthermal controller. Now they have that in there. So when each case controller gets a defrost signal and goes into defrost, you could set case A, B, and C at 80% open. You can set case D and E at 90% open, and case F at 100% open. So basically, you can balance your hot gas flow through the expansion valves, that's a pretty good thing to do. We're trying to balance the gas flow through that circuit, and if you're getting into tuning that kind of defrost, it works quite well, assuming you're getting a good flow through everything, right? So
is there a certain way, what are you actually editing? Like, obviously controlling superheat when it's in refrigeration, but like when it's in hot gas, what are you actually editing? What parameters are you trying to maintain?
Well, this is Microthermo has been working with CO2 for a long time. It goes without saying, a lot of the North American design refrigerator CO2 systems, are from Quebec, Canada, and Microthermo has a big presence out there as well. It's there where it's local for a lot of people, with Parker and Microthermo out there. So they've been designing these systems since the beginning. And when the setup parameters in the case controller for CO2 application, it's basically an application there where you just basically have a setup tab. It's if you're familiar with Microthermo, when they have their plugins and control setups, it's you just give set points to the control points that they provide you, and one of those would be defrost opening position. So you can it can be open 100% in defrost like you would on a Carnot system, closed 100% in defrost like you would on a Hill Phoenix system. And if it were on a Carnot system, you could have it open during defrost and at 80%. You have just one value to place it there to wherever you want it to go. So it uses that EEV as a dual purpose position, like just the same thing as a fixed orifice, or not, sorry, an adjustable orifice balancing valve like you would in a glycol case. When we did the setups on the glycol systems, where you get adjust your balancing valves to slow down solenoids if you had the both from cycling too much. So or any hydronic system for that matter. But that's one of the big positives of a forward flow system through the expansion valve.
Is there a certain differential you're looking for when you're tweaking something like that?
Well, you're not really measuring a differential there, because you don't have the access points or probably a tool accurate enough to do it. Mm-hmm. So you kind of, this would be something I've done it. When I'm dealing with issues, you make a little adjustment here, and you're watching defrost duration times, how long it takes you to get to termination. So if you if you have a case in your lineup that's getting to termination, 10 minutes before otherwise, there's no problem choking that case off, because it's getting more than its fair share of the hot gas. So you can squeeze it down a bit, and a little from the rich and give it to the poor. So
you're basically just trying to
balance.
You're tweaking it based off the balance of the hot gas, not no other numbers, but just trying
No,
to balance it out.
not from my experiences. That's how I see it. It's just you go with what you got, and you got 2 to 3 temperature sensors and a pressure transducer for every case controller, and you see what you have on the rack, and it all comes together. Your system termination is an and you can terminate the cases individually. Actually, if one case reaches termination, the valve will close. So then, therefore, no more hot gas is used in that case. I'm pretty sure that works that way. And you can run it that way. So it just helps you balance the defrost flow.
Yeah, the one of the last stores I started up had it was the first time I've seen this defrost design. It was a rack manufacturer. It was the newer design for them. So they were taking hot gas from the TC side, and they were using a CCM valve to control the pressure on the other side of the CCM valve for the defrost header to roughly 600 pounds.
Mm-hmm. And controlling it in or controlling it out, or both?
Controlling it out. So they were controlling the actual defrost header to 600 psi, and then they were going in the suction line. They would shut the EEPRs. They would go in the suction line, and then they would go reverse flow through the coils. Now, in this system, I am not a fan of, because it has the check valves in there, and I mean, me and you talked about it, Michael, the massive amount of check valve failures we had, but it would go through the coil like a standard defrost, go through the check valve, and then back into the flash tank.
Mm-hmm.
So
yeah. No, I know the system you're talking about as well, and I think the check valve issue is not a system issue for that one. So I don't think if you have any deterrence of that system, it's more towards that choice or design of check valve, because I know that exact system. I can't 1, 2, 3. Actually, we have a rack at the shop now that's coming. We've got a few systems out there with that exact system, with the equipment that is equipped with the check valves for the reverse flow. Is a different manufacturer than the one you were dealing with, and we've had little to no failures as far as that. So that the system I'm not sure if the exact system that you're dealing with is the same one I am, but it regulates a hot gas header by regulating pressure in and out. There's 2 regulators there, one mechanical, I believe, and one electronic, but it's doing the same purpose. It's taking the abundance of high pressure and hotter discharge gas off the TC side and forming it or keeping it in a hot gas header for supply down the lines. And when it goes down there, you usually have not a lot of problems with volume, and temperature is pretty good. So those the check valve issue, I think that's maybe isolated to one choice of design or whatever that's in there, but that type of system I've seen a few times, and it works quite well as well. Then the hot gas off the low temp discharge, because again this is again in a system that's running with the line sets, and the equipment outside the machine room is all pretty much standard refrigeration equipment and parts, not high pressure CO2 stuff, but which typically I say 45 bar and under, which is everything now is, most things now in normal refrigeration is 45 bar, and that started with when 410A came out 15-20 years ago, whatever. They upped the pressures from the old R12 and 502 days on everything. So most standard refrigeration components are rated at 45 bar now, typically. Some are a lot less, but typically that's where they are. And when you have those limitations, you got to keep those pressures down, and that system works well. And there are a few manufacturers doing systems like that. And it's with that stuff that there's various patents and various systems working with that, and they're coming together with it, and it's they're making making good changes for the system to get the defrost working better.
Finally, I think after 18 failed check valves, we convinced them to put in 4 bolts.
Oh yeah,
and I don't think we've had a coil check valve failure yet.
That's good.
Yeah, it was those stainless check valves were not a great choice for that. I mean, they were just too short, and I mean the welders were just destroying them every time they were putting them in.
I can see that as well. I've seen a few check valves in discharge, stainless check valves in. Were they stainless or were they? Yeah, stainless check valves and discharge lines on TC sides fail. Quite a few actually, and maybe the same manufacturer of those ones you're talking about. I'm not sure, but I've seen those fail again and again. It's like, did they die or were they murdered? Right? It's always the question. What you say in that. So if you're, if you abuse any equipment, it's you give a manufacturer a piece of equipment a bad name, but if it's seeing too hot of a temperature during the installation process or the welding or the TIG welding or however it's done, you're not giving it a fighting chance to work. So
I mean, some of those coils, I'll give those guys props. There's not very much room to work in there, and let alone changing it out in a freezer and TIG welding a new check valve in. I mean, I don't envy those guys. That's pretty tight in there.
Yeah. Hey, well, that system probably it's probably under 45. The bar, they could have transitioned to, if they had the right couplings, they could have went to copper and regular fittings, probably, because I'm sure It's not a 90 bar system. So, but that's
what happened.
Pardon me.
That's exactly what ended up happening.
Gotcha.
Putting it to copper, and then we ended up putting the silver soldering joints on it, putting brass 4-bolt removable check valves in. But yeah, that system seemed to work pretty good. I mean, it took a little while to get the stepper, the CCM valve that was stepping down the hot gas pressure. It seemed like it took a long time to get that tuned in. But once it was tuned in, it worked real good.
Mm-hmm. I find I like the electronics and the valves and all that, but I find when it comes to something very critical and very quick, I like spring actuated pressure regulators. It's just by the time you're communicating sensors and signals and turning a motor to the point where a spring can react, it's milliseconds. Mechanical pressure regulators really do well in those applications.
100% agree with that. Like, I would much rather have a mechanical regulator in that application than a stepper. I mean, there's just less to go wrong, less error. See, in our design that we had, there was a was it a 750 pound relief on there? It was real close. So I mean, it was in the beginning, it was chirping its relief every time we go into hot gas. I mean, it would chirp the relief. We ended up having to, when something going to hot gas, they put the valve opening to step it open like 1%, 2%, just to keep it from reacting too fast and chirping the relief. And unfortunately, there was no way to valve it off without pumping down the whole rack, because they had those new wonderful ball valves with the check valves in them, and they were all checking backwards. Well, all the suction lines were checking backwards into the defrost header from that with no way to valve it off.
That makes it too much fun.
Yeah, it's been a bit of a ride with that. So the last defrost I kind of want to go over is the 90 bar system, which I've only seen one, and it's at that pizza joint that I told you about. We built a couple years ago, and that system is full on TC hot gas, and I mean it works great.
Mm-hmm.
Like we have 2 coils in that place that are the size of Connex boxes stacked on top of each other, and it'll do both of them at the same time. And I mean, the defrost is less than 15 minutes.
Yeah, well, you're getting back into the territory of normal hot gas when you start doing that. So you get your volume and temperature, and you're not limited on pressure, so you can really just blast it like you would on just sort of HFC systems of what we're used to for the past 30 or 40 years, or however long hot gas has been around. So that brings it back to a little bit normal.
Where
So
what differential are you trying to maintain? Like when you're doing full on hot gas on the TCC? Hey guys, I want to take a break and talk about Westermeyer, one of our other sponsors. Today's episode is sponsored by Westermeyer Industries, the leader in oil management and pressure vessels for the commercial refrigeration industry.
I wouldn't. I don't think any of ours have that right now. The one full bar system, the one full system that I know it's all electric, I believe. Or no, it's all medium. There's no freezers in that site.
Okay.
Have to look at that again.
So the Mama La Rosa's pizza place, it has a floating actuator, and I believe it's trying to maintain anywhere from 50 to 75 pounds of differential on the TC side. And then it goes back through defrost, and then there's a discrete line coming back. There's a header with a discrete header with the vapors coming back down, and then it dumps them back on the other side of the valve to dump it back in the gas cooler.
Okay. That sounds a little bit similar to how I see a lot of some heat reclaim on CO2 racks work, which is it's heat reclaim on many CO2 racks is a little bit unique too, because you don't usually have the volume in your heat reclaim coils as you would in an HFC system. Usually the piping is a lot smaller, so you have to balance your flow. You have to do a bypass as opposed to a full flow. Like a HFC rack, you 2-in-1/8 discharge. You put your 2-in-1/8 discharge right into your hot water recovery tanks, or you put it right into your air handler coil, the whole shot. But with the CO2 systems, if you've got a 2-inch discharge up to your gas cooler, typically you're not running actually no, we have a couple where we ran full flow discharge up to the heat reclaim, but a lot of times you get probably 3/4-inch lines going to various stages of heat reclaim. So that's it's probably similar to the system you're talking about. You're basically using a ball valve to basically balance the flow through you use a controller to balance the flow to maintain a differential, but also not overpressure your discharge.
Yeah, that's kind of how they're doing we only have one store down here. They're using Aldi uses heat reclaim with CO2, and that's how they're doing it. They're balancing the flow, and then it's full size piping going back and forth, but they're balancing the flow still with a Bleemo valve.
Mm-hmm.
But yeah, up here so far, they're the only ones I've ever seen do heat reclaim. I mean, it's kind of like in the city of Chicago, you're not even allowed to have the standard HFC heat reclaim. So I don't see them letting us have CO2 heat reclaim.
Oh, you don't have that? No,
we're not even allowed to in the city of Chicago or like the surrounding areas. If you want to run heat reclaim on a rack, you have to have a coil that has double the operational pressure of the design refrigerant pressure. So they make it so it's almost it's so expensive to install that nobody does it anymore.
Mm-hmm.
So, I mean, but CO2 heat reclaim works pretty good. I mean, you're getting a ton of heat off that.
Mm-hmm. If your superheat's in check, though, that's where you gotta make sure you're getting that. So, your TC superheat, right? So that's the other thing with the tuning of these racks. You gotta, if you remember your transcritical suction load is a big part of a saturated gas load, albeit it's a warmer temperature, but it's still near saturated gas. So there's not a lot of superheat there, and then you do get some superheat from if you're a booster system from your low temp, and then your circuit suction lines are probably lower superheat because they're all pretty much all electronically valve controlled. So your discharge, your suction superheat can be low sometimes, lower than normal. And if you know what discharge, when you got low suction superheat, how much discharge superheat you have, or how much your discharge temperature is affected by that. You can have I've seen racks where you can put your hand on the discharge line, and it seems colder than it's colder than a lot of things around the system. So that's the discharge of a transcritical. So
Are you looking for about maybe 80 degrees of superheat on the CO2 side, on the discharge side?
Well, I think I don't know if you're looking for a minimum. You're looking for whatever you can get. It's really your discharge temperature isn't your target. It's your suction temperature is your target, is what you're maintaining, and maintaining a good and a safe suction temperature is what's going to give you your discharge temperature. Like any vapor compression system, it's kind of you want to maintain good suction superheat for compressor cooling, for oil viscosity, and then you don't want it too high and you don't want it too low. You want it just about right. And then when it's just about right, you'll get your calculated your discharge temperature. You'll be able to you'll get it out of there. But a poorly run system is going to be hot as anything, great for heat, but not good for valves and oil and efficiency and all that. But it's darn warm. So
yeah, it seems like when you get about like 10 degrees superheat return, it seems like that oil starts moving like no other. You start mixing with the CO2.
Well, that's it, right?
Yeah, then starts your oil problems.
Mm-hmm.
So, it seems you get to really control that return gas temp. You really keep an eye on that. It seems like, especially when you start with microthermal, you start seeing more oil pulses. You usually, once you start seeing that, usually some liquid floodbacks behind there too, it seems like.
Mm-hmm. Well, that's always a good thing with the industry is caught up now with the oil systems on the compressor. Just switching gears a bit over to the oil system on the compressors. The original systems, they were pretty much homemade solenoids and level switches, basically homemade Trax oils, if you will, for that, because the equipment wasn't there. Now the manufacturers, whether they're the Emerson Trax oils or the Emerson OMB lines or the Crewan lines, they do it all incorporated now of what you have with an electronic oil fill. But seeing when you have visibility of the oil pulses and the oil level, it's a really good tool for when it comes to diagnosing oil problems, like you wouldn't have on a rack with an HFC rack with oil pots, or just standard oil level controls and OMBs or Trax oils, and that you don't know what's going on. You don't know when oil's coming in. You don't know when the compressor's up and down. But when you have these systems on the older system, which unfortunately they're kind of going away now, but because we're going back to the standard components. But when you get to see that, it's just more data you can use as a technician to diagnose issues.
Yeah, I love the new setup with the OMBs and the Crevons. I really wish that they would incorporate like a dry contact closure to, say when oil's on, when oil's off. That way it can be tied into the EMS system. Because like you said, that is a great tool. So what would you say is a high pulse count? So like on a daily for a compressor, like a low temp compressor, what would you say a high pulse count to you would be? I know it's really dependent on the ambient and the system and everything else.
Yeah, well, it depends on the runtime of the compressor, really, right? So, and also with that, it depends on the solenoid and the orifice of how much oil is getting in there, and it's kind of, I'm just trying to think about that now. Because usually when it comes to those type of questions, I don't typically run them as a rule of thumb, because I find a lot of sites are different, and I generally would just compare history. Like if I were to look at a compressor and if this is what it was doing this time last week, last month, and the month before that, and now starting 2 weeks ago, it started doubling the amount of pulses, that I typically use that as a comparison. And again, the pulse count for those, it can show you if you got a pumper or you got some valve plates or some recompression in there, or even the opposite. You got You can have a pulse count, or you can have. I'm trying to think of it now. Too many pulses, which could even point as a bad relay, because it's a solenoid and a relay for those systems. So they're small solid state relays. So those solid state relays sometimes give up the ghost, and they pulse more than on the computer than they're physically actually doing. So that's always a key pointer to look at as well. So
they do.
I didn't really answer the question, but as far as a pulse count, I can't really say I'd even look or consider that as a rule of thumb type thing. I generally look at it as a system history and judge it based on the past of how it operated before and what the compressors next to it and alongside it are doing. It just basically use comparisons from what's on site. So
yeah, I agree with that. I mean, especially if you got the data. I mean, that's the nice thing about microthermals, having the data. I mean, some of the other manufacturers where we only get a week's worth of data, it's not the greatest. But yeah, the OMBs have definitely been like a step up.
Mm-hmm.
I tend to like the Crevon ones more, because at least you can get in there with an app and you can Bluetooth to them and see like how many pulses they are doing.
Mm-hmm.
That seems to be working pretty good. You guys haven't made those out there yet?
Yeah, we have some of those, and they're actually they're pretty slick too, because you can adjust them based on your oil pressure. So if you have a higher pressure oil pressure system, you can tune them. You can actually tune your oil fill valve just to have you can time how long your pulse width is going to be for your solenoid, and you can tune that valve depending on of how much or how quick or how slow you want it to pulse the oil in there. You don't want it to go in too fast for you don't want turbulence in there. You don't want foam, and you can change, you can increase and shorten your pulse width and your control settings for that. And when it comes into that, the manufacturers of that part, they've got it. They're a good resource for what they can tell you. They can help you when it comes to that, as far as looking at what type of system you have or where they think you should start or where it would be. Typically, if you have those parts right out of the box, put them on, you're going to want to tune them to where they need to be or where the old one was as a starting point, because what it is out of the box may not be suitable for your CO2 application, or it may be. It depends on the actual settings of that actual Crevon control.
Yeah. Now, how have you guys? I mean, I've seen a couple different kind of drain systems. So, like up here, like obviously Hill Phoenix does. They do a level switch in the solenoid, and that's how they drain their separator. And they, pulse the levels, or when the level switch comes up, they pulse the solenoid on. And then I've also seen how LMP does it. They do like a constant drain. So they have a pressure regulator. They set it like slightly higher than the suction pressure, and they're just constantly venting it off through their oil reservoir and then through the oil reservoir into the flash tank.
Mm-hmm.
I mean, have you guys seen anything else besides?
Yeah. Well, then there's the other one where you just basically have the higher pressure systems, where you see them a lot with Carnot, where you'll have basically your separator and reservoir. Your separator is your reservoir, and then your oil fill solenoids are piped straight off of that from high pressure. So your oil injection, your oil going into your compressor is coming in at TC pressure, or oil to your solenoid valve or to your inlet valve is actually at from the discharge pressure coming in. So that's the other one, which is probably on a couple of the systems you've seen as well. Whether it's to a solenoid or if it's into a Traxol solenoid level control.
Yeah, last two stores I started up had that, and it works. I'm just not a fan of it not having sight glasses on the oil reservoir.
Yeah, you know what? It's a challenge, and working on those systems, it's the last thing you want to do is add oil to there. If you don't know where the oil went, don't add oil. Or if you add oil to get it going, just probably plan on taking it out sooner than later, because sometimes you have to get oil to get things going, but typically in these systems the oil doesn't evaporate, it's going somewhere or it's lost somewhere. So with a not so service friendly system like that where you can't see it, the only way you can really analyze things with oil pulses and this and that, but again, that's not, you could spend hours or days deciphering data to see where you think the oil is, or look at it with the sight glass. And if you don't have that, which we're used to in a lot of systems, you can get yourself in a lot of trouble with the oil adding or subtracting oil from a system like that.
Yeah, we found ourselves in that very spot. We had I think I talked to you about it, that rack where they had us keep adding on startup, adding and adding and adding, and I ended up like 8 gallons above every other rack, and it was stuck in the accumulator.
Yeah, I've seen that as well.
Yeah, it was. We're still dealing with that. It was sticking in the accumulator because the dip tube had plugged up.
Mm-hmm.
That's what it was. It was designed with the dip tube, it just didn't have the hole, or the hole just plugged up.
Allegedly.
Or it could have been too big or something like that. It's hard to say.
A clear answer whether it has a dip tube or whether it was a weep hole.
I'd be willing to bet it's the weep hole at the bottom of the inverted trap. Suction line comes in and goes up to the top, goes down to the bottom, up to the top, and the gas comes in here, and it has your standard weep hole at the bottom of the 90 or the elbow or U bend at the bottom. It goes there. So
is it more susceptible to CO2 because of all the slag, because of all the welds?
Well, that's definitely a sore point in some of these systems, is the amount of debris that can get in there, and it's not very friendly with systems. So that could be a possibility for sure.
Yeah, usually on startup, the first liquid suction dryers are pretty rough.
Yeah.
So on industrial systems, we use a lot of strainers, like actual, removable strainers. And I mean, like, obviously you guys are dealing with a whole lot of higher pressure, but I mean, they do make, obviously, like Hansen makes valves for, CO2 and ammonia. There's no serviceable strainers that could be put in place, of these devices to make sure, like, especially on the suction coming back, right? You'd think it would get caught by the suction filter dryers unless there's not any, on the, I forget what manufacturer you said. I don't remember. Carnot.
Yeah, that's one of them. But the serviceable strainers are there. I know the first Hill Phoenix system we have has one in the drain leg from the condenser. There's basically the Y type bolt fitting service strainer that is standard, and that type of fitting that you'd see in many systems. Mm-hmm. And also a spot, you got your suction core or liquid core filters, and then another spot which is where there's a strainer is in the high pressure valve from the gas cooler to the receiver. That's depending on the valve you have there, whether it's an ICMTS valve or a CCMT or a Parker Sporlin HPV, I believe they call them. They have serviceable strainers in them, and they're a pretty good spot. Typically, they're easy to service. I know on a Carnot they are. A couple others, they're relatively, service friendly. Like you can almost take that apart and put it back together rather than quicker than you can do a lot of things on an HFC rack. So that's a good spot for, just like in a TX valve, when you have pressure differentials, it's always a good spot for picking up stuff, just like your TXV strainer. So that strainer that's on the high pressure valve is usually a great spot for getting that stuff, or at least rolling into a preventative maintenance plan for checking systems when you have time, as a just maintenance, because it's if depending on what's in your system, you're probably definitely going to have something there.
Yeah, the last two that I've seen with like plugged up high pressure valves, I noticed like I was watching the trends, and you could see like they would start, the valve percentage opens would start creeping up, and I mean flash tank pressure would stay kind of low or steady, but like head pressure and the valve percentages were like cranked way up. Like it may have been like 40% last year at this time. It was now 70 to 80%. And
which totally makes sense. You're basically got an 80-ton valve, and you're with all the crap in there. Now it's a 40-ton valve. So, you would get it like that. So,
yeah, that's one thing I like to look at on PMs. Like I like to be able to graph that out and see what it was last year at that time. I mean, just to make sure you're not plugging up and having that issue. I never pulled one apart, but did CCMT valves have strainers in them too?
Absolutely. Yeah,
okay.
a nice serviceable one. Yeah.
Yeah,
probably if I spend 10 minutes, I could probably find one in one of the milk crates behind me here in the basement. But
yeah, it's that's amazing. The other thing, Michael, if you notice like a lot of ball valves, like especially on the high pressure side, not sealing after like a year or two.
I have seen it a bit. Yeah.
Yeah, we've run into that lately. Like go to pump a rack down or go to do something and can't get it below 75, 80 pounds, is weeping through. It seems to be these racks are all like 2 years old, 3 years old. I mean, it seems kind of crazy to me that all these ball valves weep through that bad. So what do you guys do in that situation?
Well, I know one for sure that we had to repair. We basically had to dump the full charge and had the new valve. I think I ordered the valve, and we just had a valve. I wasn't on the job, but we had it was hand tigged in, and basically it's just the mechanical process of dumping a charge, tigging in a valve, and recharging the system, all with the manager on your back saying, "Is it ready yet? Is it ready yet?" So, not fun, but it got through it. But that's it's the process of getting there is it's no different than I guess any other system, because it was.
Are you guys dumping the charge, or are you pushing it into vessel?
That one, if I recall, with that one, we could. There was some of it saved and sitting. We had to dump the condenser. Pretty much dumped the condenser. Actually, come to think of it now, we're able to keep what was in the receiver. It did have a backup unit. We were able to keep the pressures down that way. And then, of course, all your freezers and your coolers, at that point they're what's keeping your CO2 from relieving. So, a full grocery store is a lot easier to service than an empty one on startup. If you get relieving and a lot of issues when you're starting up because you have no cold bank or frozen food to keep your stuff cold in the case of an emergency. But that's just basic science, I guess.
Yeah, really, with the backup units to get pushed a little more. I mean, I seen my first 2 stores of them this year. That was it. Before that, it's just been no backup units, and then we get the venting all summer long.
But I guess the backup units they're just going to slow the venting. They're not going to prevent it.
Correct.
And depends on when you crash and stop, or when the system stops. It could relieve anyways, because the backup is just a help or deter. It's not going to prevent. It's going to help. So, and that's why some customers who buy the equipment, they, depending on where they're at, or where they're located, they're not going to invest into a backup unit and a generator and all this stuff for just the sake of CO2, because what's the alternative is just relieving CO2, and the cost of CO2 is not that much. The cost of having CO2 on site can add up over time, but in sites where in cities or towns where CO2 is readily available, it's the amount of times that a backup generator or a unit is required, may not be that necessary. Now, I know locally here it's in a code. I'm pretty sure it's mandatory. You've got to have one. It's just that's what they've written into local refrigeration code, or actually it's a national code actually. So maybe all systems in Canada require it, but I don't read the code every night, so I'd have to determine that to see. I know there's a spot in there. They revised the code a few years ago with some CO2 specific information in there, and one of those is a CO2 backup refrigeration system or a generator. It's in the Canadian refrigeration code. So
Yeah, that'd be nice. Here lately, last couple of weeks, we've been having supply issues with CO2, which we usually don't have in Chicago. Like Chicago, we usually have no problem getting CO2, but like the last couple of times, I've been told, you could have 5 tanks or 8 tanks, and that's it for like, a couple of days.
Wow.
Yeah, it's they've been having some like severe supply issues here lately, so it's been kind of difficult. So we've been kind of hoarding at the shop to make sure we have some for a disaster.
I think, for hoarding is probably, I wouldn't want to say the number that our company has in its possession, but it's probably more than anyone in North America, probably. So,
So I have a question, because Kevin and I were debating this last week. We were trying to figure out the best pressure to basically have your backup or auxiliary unit running. Now, in some of the code, it says that the backup unit is only supposed to be powered under generator power, but that's not what I'm debating. Basically, I'm trying to figure out, if your high pressure is, let's just say I was working on a Cascade, and the pressure is set for, we usually run the wheelhouse about 440. The high side alarms out at 510. The reliefs blow out at 585. Where would you put your relief? Because every time I call the manufacturer, they're like, well, just set it where you think it's going to go. I'm like, but I want to set it to spec. And he's like, no, just I'm sure you'll set it right. I'm like, but I want a number. So, I mean, is there any rule of thumb, like where you're supposed to be, how far away that you're supposed to be from the actual high pressure?
well, I kind of probably have the same approach that the tech support gave you there. It depends on your system of where you want it to do its job. Do you want it to come on early? Do you want it to come on prematurely? Do you want to come on when there is a problem? Do you want to come on when there's not a problem? So use those things to decide it. So if you had it set for 500 psi, that thing might short cycle if you're running stressed, or if you got a compressor down or something like that, which isn't the end of the world. But you definitely probably want it at your alarm. If you're alarming at high pressure, you probably want that on. So and the other part about that is if it's depending on the control for the backup unit, you'd probably want to have a minimum on time. So if it you wouldn't want it bouncing on and off, which I've seen that before as well. And that, again, an oversight on a new, on a startup, when you've, the startup guys that do these jobs, are supermarkets, they're under a lot of stress and a lot of time. So, things don't always happen on day one. And, that's because they've got 18, the setting of that pressure control was item 100 on their list of item number 101, right? Which they couldn't get in the first week. So they got to 98 in the first week. So that's how things happen, which is okay. But that's how I've noticed it before. And then when you see it, you don't want it to run prematurely, and you don't want it to run too late. So if you're alarming it, if you're at a point where you're going to alarm, I would assume you'd want it to run, and you don't want it to short cycle. So that's kind of my take on that. And you don't want it on too late either. So I'm assuming you're dealing with a mechanical pressure switch that turns it on.
Yeah, that's basically the fail safe.
Yeah.
So like I said, the EMS is set for 510. So I just didn't know, because each one of these that we've taken over for warranty basically has been, the compressor has been smoked, whether the discharge check valve has failed because of short cycling, whether they couldn't, more than likely they couldn't get the cascade pressure down. So they're like, well, we'll just turn down the pressure switch and just let it run. They think they had it set for one point and I think it was 330 psi, which is way too low for that system. You know what I mean? So you're basically, you know.
Yep, I think he muted himself.
Yeah. So I think I know what he was saying there. He basically having a system too low, and at that point, your backup unit becomes part of your refrigeration system. So that's not what you want it to do either, because it's not designed for that. It's not, I don't think it depends on where that's running. It's not gonna, again, that's like any other single refrigeration system. It's got to be, working too low. It'll either be smoked with low. It could start to flood. It could, depends on how that backup unit is set or commissioned and how it's working. You definitely don't want it to be running constantly or short cycling. So with that in mind, that's where you're going to want to keep your focus on your cut-in point, that with the mechanical control.
Sorry, technical difficulties. I don't get nice hotels like Kevin. So basically, I think I just touched the outlet with my foot, and it just shut down all my equipment.
That's all right. You're back. Did you hear what I said?
Yes.
Okay, all right. So I was kind of thinking that's probably where you're going with your low pressure operation of that. So, and again, like anything when it comes to that type of system, whether the OEM designs some sort of fail safe or monitoring at that point, it's always nice to have some sort of input, digital or analog, or some sort of current sensing of that unit. So, if you have that system running, for even a proof run, if you have a 10-minute or a 5-minute proof run on your auxiliary unit, like, it should trigger an alarm. And if it's triggering an alarm when you're in an emergency situation, who cares? It's when if it triggers an alarm when everything's running normal, that's when it can come up. So that's, just adding to whatever controller you have to prevent that, or even some sort of, monitoring point to monitor its operation. So to tweak it. So that's always something.
Well, that's where the confusion lies, because I mean, they're telling me that this thing, like per the prints, it says that it's supposed to have its own generator. So technically, it shouldn't be running right now, but it is running.
Well, yeah, and typically it's on a transfer switch, though. It will be on a generator.
Mm-hmm.
That generator, it's probably on a panel that's it's on grid power. It's on your normal supply power, but when the power goes out, there'll be a transfer switch that will energize another panel, and that compressor would be on that panel. So it's powered with the grid.
Whether you have a failure on the generator or where you have to switch to generator power, or you have a failure for whatever, if it needs it, it's going to be on. Yeah.
Well, so the generator's not going to run unless there's a power outage. Period, right? And a lot of the time, depending on, again, that's the building code. Like, a lot of times you'll have depend on where your construction building code, a common name is a life safety generator. So, you'll have a generator in the building. It would do certain lights. It would do certain, maybe the computer or a server or phone lines, and different loads, electrical loads in the building would be on this life safety panel. And when that, it could be running on that, or it could be a shared load on that generator. It could be a specific generator just for the for that generator alone, or refrigeration purposes. I've seen both. That generator used as a transfer switch, and on the transfer switch, I think you get the control circuit power, the computer power, some control board, like remote control board power. So in the event of a power outage, you still get your computer, you still get your control circuit, you'll get your generator and your backup units, so you can continue to log and service things or dial in and look at that. So, and then I've known for some that are on a life safety generator. So, you'll have a 50 or 100 kilowatt generator in the store that does the lights, or an elevator or whatever for the store, and then that 10 or 20 kilowatt load for the backup unit would be on that generator. So that's all depend on the architect or the electrical engineer, how they design the building and the local codes. So when it gets into that, you do get into, every jurisdiction may have different rules. So
Gotcha.
Mm-hmm.
Well, Mike, on that note, I can't appreciate you enough to be on here. I really appreciate you taking the time to come out and be on tonight. It really means a lot, man.
Yeah, no problem.
I mean, we really appreciate you going through all this stuff with us, and hope to get you on again sometime soon.
Yeah, for sure.
So,
Hey.
All right, guys, have a nice night. Thanks for listening.
Thanks again, Mike.
All right, cheers.